Hello and welcome to today's tutorial. So today we're going to talk on the random process, and we'll understand what is random process, what is its stationarity, and what is first order stationary random process, and so on. So let us switch back to our screen and let us see the definition of a random process. So there are many definitions of random process here. So basically a random process is one where if the random variable depends on the function of time t, it is called as a random process. So if we can see this first definition from here, we can see that if random variable, if it is a function of time, then it is called as a random process. Likewise, there is one more definition here. When the random variable is a function of one independent variable, that is time t, it is called as random process, that is denoted as capital X of t. And the random signals generated at multiple points are collectively called as random process. This is one more definition. So likewise there are many definitions. So before going further, so let us revise quickly what is a random variable and what is an observation and all these things. For example, we have conducted an experiment. So we have a sample space here, tossing a coin, tossing two coins, and the expected outcomes here. So we have four outcomes from these two coins, that is either we'll get head head, head tail, tail head, and tail tail, and its outcomes are allocated with an observation, say xa. So now I'll take a case where, so x1, I'll define the at least one head or the two heads. So here I'll be having one. Okay, let me take like this. um, so here the first observation I will define, if there are two heads, I'll call this as 2. So let me call this as x2, and if there is one head, x1, I'll call it as 1, and if there are no heads, okay, this has become reverse, so let me give a new observation for this. So the new observations are, let me go like this. So first observation, say xa is the first observation where the two heads are there in the outcome, so I'll give the value as 1. So if there is one head, I'll give the value as 2, and if there are no heads, again it has become the same thing. Let me go like this, let me delete this again. So let us take the first observation xa as no heads, so it is 0. Then one head, I'll take it as 1, and if there are three heads, I'll call it as, sorry, if there are two heads, then I'll call it as 2. Now what happened, these four outcomes are mapped to three observations. So now we have the three observations, that is 0, that is 1, and 2. So all these observations are integers. So if I write this in terms of the cumulative distribution function, then it is written as a probability of x of a, which is less than or equal to x. So this small x represents the observation here, and if that value is less than or equal to a random variable capital X, then its probability of all this defines the cumulative distribution function. Likewise, to define the probability density function, if I differentiate this d by d with respect to any observation x, a, x, b, and xe, so then I'll get my PDF, the density function, that is fx of x. So this, I'll get this as, that is denoted as a small f x of x. So this is fine if you are talking about the single value of observation, that is an integer value. Now if this observation, if it is a continuous function of time t, so then it is not one value, then we will get a graph something like this, which is a continuous variation with respect to time t. So here likewise we have three different observations which we obtain. So this we can conduct, we can consider this is an experiment observations. For example, this might be a recording of pressure or a temperature of a day. So for example, this might be an observation of a day, of a variation in temperature, say from morning till evening. So again the next day we have taken one more recording of the same city of temperature variations, say from morning till evening of same timing. So again, third day we have taken an observation of say this temperature again from morning till evening. So to understand this n symbol, so there is one concept called n symbol. N symbol is nothing but an averaging of all these observations at one particular say time t1. So now there are certain values here. Now this is defined as, if this is my x1 observation, this is x2 observation, x3 observation. So this is a time t1, so this point we call it as x1 of t1. So this another sample point here, that is x2 of t1, and here this is called as x3 of t1. So this is one sample point. So likewise, if I take one more sample point here, so this is another observation, this is x1 of t2. This is at another time instance, say at t2 if I take, so this is another sample space that will be created here. So this is x2 of t2 and x uh, 3 of t2 likewise. So this can be called as x of t1. All the average points of this is called as x of t1, and this might be called as x of t2. So this, like this, if we have the n observations here, so averaging of all these is called as an n symbol. So n symbol is a very important concept which is used in the random process. So hope you have understood the definition of n symbol. Now let us come back here and let us see the definition of n symbol. Now a random process or a stochastic process is an n symbol or a sample space. Such sample space consists of the sample points whose outcome is a random function of time. Now that is what we have seen one example there. An n symbol for a random process, say x of t, is a collection of sample functions x1 of t, x2 of t up to xn of t, or the outcomes. Likewise, this is x1 of t, x2 of t, and x3 of t. Like this, if we have xn of t, so such observations or the random process of x of t and a time t equal to t1. So then at time t equal to tp, then this set, it will form a set of numbers, say x1 of tp, x2 of tp, xn of tp is a random variable of that particular. Now it has become random variable. Individual values are called as random variable. In totality, if we combine all these random variables, then it is called as a sample space or n symbol space. So now let us look into its probability density function. Let me save this page here. So let me call this as page 1. Let me take a new page. So now let us see the probability density function, that is PDF. The probability density function, in short it is called as PDF. So before going to PDF, we will see the probability density function. So we know that the representation of the CDF, it is defined as fx of x for a random variable. Now if you want to define this for a random process, how do we define it? So the first order, the first order distribution function if you define the first order distribution function, then associated with, say, a random process at one particular time t1 that you have seen in the previous example, we have taken the observations where we have taken at one point, that is t1, and all these points are nothing but the random variable. Collection of this is called as a random process or an n symbol. So if I take this at one particular point, that is the first order distribution with respect to time t1, then its CDF is denoted as, like random variable, it can be represented as fx of at time t1 of x1. So this can also be called as x1, and if we take the another sample here at time t2, just for simplicity we can call this as x2. Please do not get confused with this x1 with the symbol x1 and x2. Okay, so these are different things. So this is the given at that instant. So the distribution function, that is fx of t1 of x1, is defined as a probability of that random process at particular time t1 less than or equal to that observation value, that is x1. So this equation we call it as a first order distribution function. Now if I define the second order distribution function, second order distribution function, then now it is with respect to two time instant, that is t1 and t2, that is here the t1 and t2s. Then how do we define this? So that is defined as fx of the two time instants, that is fx of t1. Now it is a collection of two n symbol process. So now this is one collection of set and this is the another collection of set. Okay, so this is one collection of set of these points and this is another collection of set of the points. Therefore it is fx of t1 with fx of t2 of x1 and x2 is equal to, it is a probability of x of t1 which is less than or equal to the observation x1, and this is x of t2 which is less than or equal to x2 observation, or this average of x2. So this is the joint distribution function for the second order. Similarly, if we write this for the nth order, let me move this section here. So likewise, if we create for nth order random variable, then its distribution function continues like the fx of t1, fx x of t2, so on. It will continue with the sets up to tn of the x1 collection, x2 up to xn, which is equal to its probability of x of t1 is less than or equal to, say, x1. Then I'll write down here, then it is x of t2 which is less than or equal to x2, and so on. It will continue. Likewise, x of tn is less than or equal to xn. So this is how we will define our distribution function. Now if you want to define this distribution function with our say density function, then that is defined as, let me save this page here. So this is page 2. So let me take a new page. Then the distribution function, the density function, we will get it by differentiating the distribution function. For the first order, we will get fx of, say, t1 of x1 is equal to differentiating with respect to the first observation x1 with fx of t1 of x, and we know from the previous definition what is our fx of t1 of x1 is nothing but the probability of x of t1 is less than or equal to x1. So this is our distribution function, and by differentiating the distribution function I'll get my density function. So likewise, if I want to get my density function for second order, then it is fx of t1 with and x of t2 of x1 x2 is defined as the derivative, the second order differentiation with respect to x1 and x2, that is my fx of t1, x of t2, of x1 and x2. So this is how we will get this. And there are few quite properties of this density function. We all know the properties of the from the random variable, the distribution function and the density function. The distribution function value, its probability will never be 0. The distribution function value is always a monotonic increasing function. Likewise, its density function is also, its value is greater than or equal to 0. The same property is applicable for the random process here. So if you write those properties, so then here we'll write one simple property quickly here, that is fx of t1 and for t2 of x1 x2, which is greater than or equal to 0, where x1 and x2 are the observations where its value range from minus infinity to plus infinity. Sorry, there is no equals here. It ranged from minus infinity to plus infinity. So this case, the second order case, is also called as a bivariate case because there are two processes, that is x of t1 process and x of t2 process. If you want to define this in terms of two different random processes, that is x of t and y of t, a special case of bivariate case, so then this can also be written as fx of t1 with y and the random process t2 can be defined as x1 y2, which is greater than or equal to 0. This is a special case of a bivariate case where we have two different random processes, whereas here we have the two random process of same variable name, that is x, but at two different time instants, so we have two different n symbols sets. Okay, so likewise we can define this for the density function for nth order. So hope you have understood. So same thing if you continue this for fx of t1, x of t2 dash up to x of tn of x1, x2, xn, which is greater than or equal to 0. Okay, so in the next tutorial I'm going to talk about the independence case in terms of the random process, and then we will talk about the expectation of a random process. So thank you for watching this tutorial. So catch me in the next tutorial.